Welcome everyone to the next Gen 4 International Forum webinar presentation. Today's presentation on analysis of the reactivity loss of the Phenix core cycles for the experimental validation of the DARWIN-FR code package will be presented shortly by Mr. Victor Villon. Doing the introduction today is Dr. Patricia Pavier. Patricia is the chair of the Gen 4 International Forum Education and Training Working Group. She's also the National Technical Director of the Molten Salt Reactor Program for the Department of Energy, Office of Nuclear Energy. Patricia.
Thank you very much, Berta. Good morning, good evening, everyone. It's a pleasure to have Victor Villon with us today. He is the winner of the 2023 Pitch Your Gen 4 Research Competition. So congratulations, Victor. Victor is a PhD student in the Research Institute for Nuclear Energy System for Low Carbon Energy Production at the Commissariat à l'Énergie Atomique et aux Énergies Alternatives, the center of Cadarache in France. After graduating with a master's degree in mechanics and specializing in nuclear risk management, he pursued an advanced graduate degree in nuclear engineering at the French Institute for Energy and Health Technologies to specialize in neutronics with the goal of pursuing a career in research and development after earning his PhD. So without any delay, Victor, I give you the floor. Looking forward to listening to this webinar. Thank you very much.
Thank you for the introduction and for inviting me for this presentation. And also, thank you for listening me talking about my research on sodium fast reactor analysis. Before presenting the structure of the presentation, I will give you a little bit of context that will allow understanding the different parts. So in a very large context of future reactor development, some prototypes or design will need to be produced, where Gen 4 technology will be part of. And those technologies will need to be compliant with safety requirements and economically viable. For that, you will need to characterize your reactor to be sure that they respect your safety margins and design margins. For that, you will use scientific computational tools that will, scientific computational tools that will need to be reliable and with known uncertainties. And the process to evaluate this reliability and those uncertainties is called VVUQ. So for verification, validation, and uncertainty quantification. And for that, you need to compare the results of your computational tools with a representative experiment for every phenomenon inside the reactor. And in this project, we want to go further. We want to use the experimental value to improve the nuclear data, which is called data assimilation. And why is this important? Because nuclear data are the input data of the different SCTs, so that the reliability and the uncertainties are directly depending on the reliability of the nuclear data. And in today's topic, I will focus not on design and development of future reactor, but only on VVUQ and data assimilation for a specific coefficient in sodium fast reactor, the reactivity loss. So why reactivity loss? Because it's related to the time cycle, so directly to core economics. Because it's also related to the end of cycle core characterization, so directly to the safety, sodium void coefficient for those who know, and because it can potentially provide information for fast fission yield, so a more scientific purpose. So the structure of the presentation will be then to explain, how to compute the reactivity loss with which scientific computational tool. These tools will be the DARWIN-FR code package. We will then need to interpret, to determine the experimental value and the uncertainty of the reactivity loss for our experiment, which is the Phenix core cycles. And during all this VVUQ process, we need to know what's the nuclear data uncertainties. For that, we will need a specific formalism for that. And to go from the VUQ to data assimilation, we need to answer a certain amount of question like, is the experimental uncertainty low enough compared to nuclear data uncertainties? And if the bias from the DARWIN-FR code package are sufficiently low compared to nuclear data uncertainties. So the structure of the presentation will be to highlight each part of this diagram, starting with how to compute the reactivity loss coefficient. So before explaining how to compute reactivity loss, we need first to define what's reactivity loss in a more physical way. For that, I will need to introduce some neutronics vocabulary. And inside the reactor, one of the most important characteristic is the multiplication factor, which is the number of neutrons produced by fission under the number of neutrons absorbed and leaked. So it's directly related to the chain reaction. And in fact, we are not using directly the multiplication factor, but the reactivity, which is the same, but in a more convenient unit. And when the chain reaction is self-sustained, like when you have a multiplication factor of exactly 1 or reactivity equal to 0, you have a self-sustaining chain reaction, and your reactor is called critical. So when you have a reactivity higher than 0, you are in a hypercritical state and the power increases. And when the reactivity is below 0, you are in a subcritical state and your power decreases or is equal to 0. So now let's build our reactor. So for that, you will need some fissile material. Now we called reactivity excess the hypothetical supercritical state that would have this reactor with only fissile material. Of course, in the real life, this reactor does not exist because it will be destroyed instantly. Mostly because you need to temper the reactivity excess from the fissile material, and for that you need a strong absorbing part, bring in classical sodium fast reactor by control rods. So when your control rods are fully inserted inside your reactor, you are in a subcritical state, a high subcritical state, and you are at 0 power. And as you can move the control rods, you can pilot the reactor reactivity with them so that you can reach the criticality, so that the reactivity excess is equal to the control rod worth inside the reactor. Your reactivity is equal to 0. And in fact, in neutronics, at least neutronics for reactor physics, is how and how much is the reactivity affected. So how and how much the reactivity excess will be affected by temperature, isotopic composition evolution, etc. And how and how much will be, how and how much is the control rod worth and how it's affecting the reactivity excess. So now we have a reactor, a critical reactor. So I will use. We have a critical reactor, but at 0 power and cold temperature. So in a real reactor context, at least a power reactor, we want to increase the power to be sure to produce heat and or electricity. So for that, we will extract the control rod. This extraction will induce a hypercritical state. This will be lower than the reactivity excess, so the power will increase. By increasing, the power will increase the temperature, and with some physical phenomenon like Doppler effect or thermal expansion, all grouped as feedback, the increase of the temperature will affect the reactivity excess, which will decrease. And this decrease will equalize the control rod worth so that you are in a critical state again, but at a higher power. So for example, at full power, if your reactor is at 500 megawatts. So now you are producing power. What happens? So what happens? You are producing heat power by fissioning fissile material, which means that you are losing some fissile material and that you are producing some what we will call waste, so fission products and minor actinides. this decreasing of fissile material and your production of fission products, etc., will affect the reactivity excess negatively. So you will lose some reactivity excess. In fact, reactivity loss is the reactivity excess decrease by the isotopic composition evolution, so by fuel depletion. And of course, in a real reactor context, to maintain criticality, you will extract your control rod during all the cycle. And why it's important, or why it's interesting to study the reactivity loss, because fuel depletion is related to isotopic composition. So study reactivity loss allows to indirectly evaluate the final isotopic composition, which is important for safety studies. And because during the fuel depletion, you will have lots of phenomenon and interesting to evaluate, like is the feedback change during irradiation, etc. So now that reactivity loss is more clear, I hope, how to compute reactivity loss. So as I said, reactivity loss is related to isotopic composition evolution, and the isotopic composition evolution is governed by the Bateman equation, which depends on some input data and the neutron flux. And this neutron flux is governed by the Boltzmann equation, which depends also on some input data and the isotopic composition. So it's a coupled problem, and to solve this coupled equation, we use the quasi-static hypothesis, which means that we remove the time dependency of the Boltzmann equation and we use the neutron flux constantly in the Bateman as a constant in the Bateman equation. So in practice, how are we doing that? So first, we need to determine the initial neutron flux and the initial multiplication factor. For that, we need an initial isotopic composition, input data called some nuclear data called cross-section for the Boltzmann equation, and the given geometry. With that and with a solver that solves the Boltzmann equation, you can obtain the initial neutron flux that you can give to the Bateman equation to compute the next isotopic composition. And by doing that, you can evaluate the evolution of the neutron flux and the multiplication factor. But is that all? No, because as I said in the last slide, in neutronics, temperature has an impact on the cross-section with the Doppler effect and on the geometry with thermal expansion. And this impact of the temperature on the neutron flux, so on the power, will impact the temperature map and so the power. So you need to couple the problem with the other physics and not just neutronics. So you need to add the coupled equation from thermal hydraulics, thermomechanics, and fuel behavior to take into consideration the right temperature map inside the core and the dependency with the neutron flux. So in practice, you just to add an additional iteration loop to obtain this dependency. And at the end, you can obtain the evolution of the multiplication factor. So the evolution of the reactivity through irradiation time. And what we want to determine is the reactivity loss coefficient, which is just the derivative of the reactivity evolution through time. Now, imagine that you are able to solve each equation evolved in this coupled problem with the reference method. You will obtain a high fidelity modeling, which is not reachable now for classical computing power. So we need to add some assumptions on the way that we are solving the different equations. So in our case, for the Boltzmann equation, we are using the Apollo 3 FR, so fast reactor neutronic deterministic scheme for the Boltzmann equation, and we are using the Mendel solver for the Bateman equation. So those two codes coupled each other is called the DARWIN-FR code package. So when I'm talking about the DARWIN-FR code package, I'm talking about the coupling between Apollo 3 fast reactor and the Mendel solver. And for the multi-physics, I will call all the physics outside neutronics multi-physics, as I'm more focused on the neutronic side. So for the multi-physics equation, we use the Germinal V2 code, which is the fuel performance specifically developed and validate for sodium fast reactor fuel. So by using DARWIN-FR code package and Germinal v2, we have our best estimate modeling, and we can compute the reactivity loss coefficient of a given reactor. So now we need to define, we need to found an application, a power reactor application to assess this methodology. And for that, we will need a sodium fast reactor that has sufficiently long cycle at stable power and sufficiently high power. And those experiments are quite few for sodium fast reactor, but hopefully in France we have the Phenix reactor, which was a pool type sodium cooled fast reactor of 563 megawatts, which is enough to observe a significant fuel depletion and then significant reactivity loss. It has been operated through more than 50 cycles. So in these 50 cycles, we will have some enough experimental feedback to assess our tool. In fact, to determine the cycle that we want to study, we have two criteria. The first one being a cycle at which is power stability. We need a cycle at constant power, and we need a control rod weight experiment at the beginning of cycle, and we'll see later why. But we have in these 50 cycles, we have decided to simulate the cycle 42. 42. And you can see the geometry modeling of the Apollo 3 tool for the cycle 42, for the Phenix cycle 42. So a Phenix core is a complex object to represent because you have in-core experimental device, complex in-core experimental device that will affect significantly the neutronics inside the core. You have moving control rods, and you will have a significant impact of the multiphysics as the Phenix reactor is a power reactor. But our best estimate modeling is able to represent all of these points. So with our best estimate modeling, we can obtain our best estimate value, which is for the reactivity loss coefficient, minus 4.65 cents per EFPD. So EFPD is for equivalent full power day. So if you are operating at full power, EFPD is equal to days. So in fact, it's minus 4.65 cents per day, approximately. But what's the value of, what's the reliability of this value? So to estimate that, we need to make a bias decomposition. And before to making actually this bias decomposition, I will need to introduce some vocabulary. So imagine that you have the real value of the experimental reactivity loss. So the experimental value without any uncertainties. And you have a high fidelity modeling that is perfectly solving the different equation. Even in that case, we will not obtain the exact same value as we are using input data. So we are using nuclear data that have uncertainties. And these uncertainties will have a direct impact on the computed value, and you will induce a given bias to this computed value. This bias coming from the nuclear data uncertainties is called uncertainty, and it's what we want to know when we are making making uncertainty quantification. But we are not yet in that case because we don't have high fidelity modeling. We have our best estimate modeling that is based on several assumptions. And each of these assumptions will induce an error on the calculated value. So we need to estimate this error. And in fact, those errors from assumptions inside the computational tool are called epistemic uncertainties. And bias decomposition is the process of estimating the epistemic uncertainties. For that, we need to list every assumptions that we have made and to directly or indirectly estimate the impact of such hypothesis on the reactivity loss coefficient. So I will not focus on each of these assumptions, but I will mainly focus on two of them. So first, the bias induced by the initial isotopic composition. So we are modeling the cycle 42, but that means that we have 41 cycles before, so that at the beginning of the cycle 42, all subassembly are already irradiated, so that you don't know experimentally the the isotopic composition? We don't know, but we have a computed database which is validated towards the beginning of cycle reactivity, which means that we are quite confident about the isotopic composition given by this database. So we consider that the bias induced by the isotopic composition initialization with this database is negligible on the reactivity loss coefficient. The second one is, and the most important one, is the intrinsic bias of the Apollo 3 neutronic deterministic scheme on the neutron flux. We know that deterministic computational tools have some assumptions that will induce an intrinsic bias on neutron flux, and as in the fuel depletion loop, we use this bias flux to produce the next isotopic composition. We'll have biased isotopic composition that will bias even more the neutron flux, etc. So to estimate this bias coming from the Apollo 3 FR package, we have made at beginning of cycle a reaction rate comparison between this scheme with the reference tool. So it needs to be investigated more in depth because we need to propagate this initial bias towards the reactivity loss coefficient. But in first order, we can consider that this bias is negligible for reactivity loss coefficient. So good news, at this stage, we have our best estimate value for the cycle 42. And this value is considered as unbiased. Now we need to compare this value with the experimental one to observe how far we are from the real value, the reliability. So how to compute the experimental reactivity loss? For that, we need to remember that during irradiation, the reactivity loss is always compensated by the control rod, by the control rod extraction. In the Phenix reactor, the control rods are used all together. So we are calling them when they are together rod bank. So during irradiation, the rod bank compensate the reactivity loss so that the reactivity loss is exactly equal to the rod bank worth between the beginning of cycle and the end of cycle axial position. And it's a good news because reactivity loss is not measurable experimentally, but the rod bank worth, yes. So we need to define two different things. What's the evolution of the axial position during irradiation, and what's the rod bank worth through axial axis? So let's begin by the axial position history. So the axial position history of the rod bank through irradiation cycle is foundable inside the cycle reports. So we have them, but the axial position inside those reports are the one in the operator room that was printed in the operator room, which was the one at a cold state, at an equivalent cold state. But as the Phenix reactor is a power reactor, you have thermal expansion. So all the different sizes will increase, and the result of all this thermal expansion is that the control rods are slightly inserted inside the reactor. So in the cycle report, you will have this axial position, but in the reality during irradiation, the axial position would be in this position. So we need a formula to correct this axial position, and we have a phenomenological law depending on the temperature rise, the sodium temperature rise inside the core, and the temperature of the rotating plug where the control rods are fixed. So we have the different coefficients and the different parameter of this thermal expansion law, so we can update this the axial position history. So now we need to determine the rod bank worth through axial position. So unfortunately, again, it's not possible to directly measure the rod bank worth in the upper part of the core, but we can measure the individual control rod worth of each control rod, and then transform all of these individual control rod worth to the rod bank worth. As the control rods are interacting each other. This interaction is called shadow effect, and due to this interaction, the rod bang worth is not equal to direct sum of each individual control rod worth, and we need what is called the shadow effect coefficient and the given formula to transform that. So we can have the reactivity, the shadow effect coefficient. We have the formula. We just need each individual control rod worth to obtain the rod bang worth. So now the question is then how to obtain all of this value experimentally. So for that, we need a control rod worth experiment called weight by balancing in Phenix, and it was this reason for that we needed an experimental control rod worth at beginning of cycle, because we need this value to estimate the reactivity loss at the end. And we have chosen the cycle 42 because there was this type of experiment at the beginning of cycle. So how it was possible to perform such a measurement? So you take one control rod that you fully insert inside the core. You take the other one that you fully extract outside the core, and you position the other one so that the reactor is critical. So in this at this step, you are at 0 power, cold temperature, and you are critical. In that state, you will slightly extract one control rod, and this extraction will induce a positive reactivity that will increase the counting weight inside the fission chamber. And from this increasing counting weight, we can, with a reactimeter based on an input data, obtain the reactivity change induced by this extraction. And by doing that for each control rod, we can obtain the reactivity change for each part of each control rod and rebuild the individual control rod worth. So we have every part of the global scheme. So from the individual control rod worth to the reactivity loss curve. But this methodology suffered from some limitation, as for example, the input data for the reactimeter, so the delay neutron fraction, was considered as constant and the same for every cycles. The shadow effect coefficient was considered as actually constant and constant for every cycle also. And thermal expansion was not considered for weight balancing. That means that those two axial positions were not correcting during weight balancing. And the main important parameter is that no uncertainty was given with this value. So what we have done during this work is to update the different value considered as constant. So we have updated with modern reference tool, the beta, the shadow effect coefficient, and we have introduced the thermal expansion during weight balancing. By doing that, we have changed the experimental value by 20%. So the original bias was quite huge, but it was not a problem at that time because it was for operational purpose. But here it's for analysis purpose. So we need reliable experimental value. We need clean experimental value. So we have updated this value, and if we compare the calculated value with this the updated value, we are far from 0.75% from the experimental value. So it's a kind of good result that we need to compare to the experimental uncertainty that we need to quantify. And how to quantify the experimental uncertainty? So for that, we have made an uncertainty propagation via a Monte Carlo method, which means that we will sample the different input data that have uncertainties. So in our case, we have done it 200,000 times so that we obtain 200,000 reactivity loss curve. The average of this all of this sampling is the previous curve, and the standard deviation of all of these samples is the experimental uncertainties. So to perform that, we have used for input data that where we know the uncertainties, we have used the given uncertainty and the correct distribution around the average value. And for unknown uncertainties, we have used conservative uncertainties with a uniform distribution, which is a conservative distribution. So that the final result of this uncertainty propagation will give an exhaustive and a conservative handling of uncertainties. So we can be quite confident about the new value and the relative and the given experimental uncertainty. So by doing that, what can we obtain? So we obtain on average, the previous curve presented before, and in the red area, the standard deviation of each point of the reactivity loss curve. And for the reactivity loss coefficient, which is the slope of this curve, we obtain an experimental uncertainty of 0.0061 cents per AFPD, which is 1.3%. If we consider that the power is perfectly known, and in fact, this power is not perfectly known, but in this work, in this presentation, I will consider that this power has zero uncertainty. In the PhD manuscript, we will talk more about the power uncertainty as this uncertainty has a specific behavior, not behavior, but it's a contributor on the computed side and on the experimental side, and the type of uncertainty of this parameter has a huge impact. So it needs to be taken differently from the other. But for now, we consider that is 0, and we have 1.3% of uncertainty. So to recapitulate, we have a best estimate value considered as unbiased. This best estimate value is 0.75 far from the new clean experimental value, which is within the experimental uncertainty range. So now we need to determine the nuclear data uncertainty associated with this best estimate value to compare it with the experimental uncertainty. So how to compute nuclear data uncertainty? In neutronics, we are using sensitivities. So what's a sensitivity? Is how a given quantity of interest is impacted by a small change in the parameter. So in our case, the quantity of interest is the reactivity loss coefficient. And we want to study the impact of changing a cross-section, a fission yield, an initial isotopic composition on the reactivity loss coefficient. And by using those sensitivities with a first-order assumption, I will not get into details about this assumption, but in neutronics these assumptions are commonly used. With these sensitivities and a covariance matrix summarizes all the uncertainties of every parameter and the correlation between them. So with the covariance matrix and the given sensitivities, we can obtain directly from a relatively simple formula called sandwich formula, the nuclear data uncertainties. And then how to compute the sensitivities. So as a first approach in neutronics, it's possible to easily obtain the sensitivity to the multiplication factor for the cross-section with the perturbation theory. So when I say easily, it's because with one calculation, we can obtain all the sensitivity directly. But with the perturbation theory is not exactly able to see what happens during fuel depletion, because it focuses only on the Boltzmann term, and as fuel depletion is a coupled problem between Boltzmann and Bateman, ignoring all the Bateman terms and everything that is related to the Bateman equation, you will miss something if you are forgetting this aspect. So we need a specific formalism called Bateman and Boltzmann coupled sensitivities, so developed in the 80s, that is able to see the direct term from the perturbation theory, but all the terms coming from the fuel depletion and the past of the final state. And so to compute all the new terms of these coupled sensitivities, you need to backtrack in time And this backtrack in time and some questions were complicated to consider in a real core context, but it's recently implemented in Apollo 3, and it will be the first time that this formalism is applied on a real power reactor, on a real 3D power reactor. So at this stage, we are able to have the sensitivity to the final multiplication factor of fuel depletion, so the end of cycle multiplication factor. But we don't exactly want the sensitivity to this multiplication factor. We want the sensitivity of the difference of multiplication factor between the beginning of cycle and the end of cycle. For that, we have a quite simple formalism called equivalent general perturbation theory that allow to obtain this kind of sensitivities with each individual sensitivities. So at this stage, we have the sensitivities, the correct sensitivities for fuel depletion, for reactivity loss. So if we want to determine the nuclear data uncertainties, we need those sensitivities and a global covariance matrix for every nuclear data used during the fuel depletion evolution problem. For the nuclear data library that we are using, so JEF 3.1.1, we have the COMAC V1 covariance matrix, which is an experimental covariance matrix. That means that you will have the correlation between each cross-section coming from the microscopic experimental measurement and the different parameters used in the model during nuclear data evaluation. So we have this COMAC V1 matrix, but only for main cross-section. And for the rest of the nuclear data, we are using what we have, so some variances with sometimes ad hoc correlation, which means that we are just respecting some physical rules as mass conservation, but we don't have the experimental correlation of everything. So if we are taking everything that we have, we obtain a global sensitivities of 7.43%, mainly handled by cross-section. And is 7% a lot for this kind of problem? So you can have an idea by compare. So 7% of uncertainty for reactivity loss is directly like 7 days of uncertainty for a 100-day cycle. So if you put yourself inside in a design mode where you want to build a reactor, having 7 days of uncertainty at full power for your reactor, if you convert those days into money, you will have the cost of this uncertainty. And it's quite a lot for power reactor. And imagine that you are taking only the sensitivities coming from the Boltzmann, from the perturbation theory, you would obtain only 2% of uncertainties. And those 2% of uncertainties are because you are missing a large amount of information coming from the coupled terms, so that using perturbation theory for fuel depletion will give you wrong results, and coupled sensitivities are mandatory for this kind of study. So to recapitulate all the VVUQ process that we have made for now, we have our best estimate value considered unbiased, which is within the uncertainty experimental range. Experimental value considered as conservative and where we have a lot of a reliable value, considered as a reliable value. And the nuclear data uncertainty is largely bigger than the experimental uncertainty. So we check this point, and this uncertainty is largely bigger than the epistemic uncertainties considered as 0. So we can go through data assimilation for the reactivity loss with the reactivity loss experimental feedback of Phenix. So what's data assimilation? Data assimilation is using the experimental value of an integral experiment to improve the knowledge of the input data with what we call Bayesian inference. And now imagine that everything that we have done before is a black box. So this fuel depletion black box gives you the best estimate value that we have computed when you are giving the JEF 3.1.1 nuclear data. And it will give you the nuclear data uncertainty that we have computed in the last part if we are giving the covariance matrix, COMAC V1, etc. Assimilation is find a new set of parameters that and a new set of uncertainty that allow to obtain exactly this value, this computed value after the output of the black box equal to the experimental one, and the propagated uncertainty equal to the experimental uncertainty. And when you are performing that, you can't do as you want. You can, for example, take only the first parameter. You change only the first parameter to obtain what you want. No, you need to respect some physical and experimental constraints, and all of these constraints are summarized inside the covariance matrix. So we have an objective and constraint, so it's a minimization problem. But the time, the simulation time for this black box is about 1 day, and the number of parameters is huge. So we can perform this minimization problem with a brute force approach, but we can use the sensitivities that we are computed in the last part. So by using sensitivities, we can, with a deterministic formalism for data assimilation, obtain when you are giving to this system the sensitivities, the experimental value, the experimental uncertainties, the calculated value, and input covariance matrix, you can obtain a posteriori nuclear data, which are the nuclear data that have learned about this reactivity loss experiment. So it will be called, you will have corrective factor and an a posteriori covariance matrix. And during this work, all this assimilation process was performed by the Conrad software. So for example, when you are using this data assimilation process with the reactivity loss and everything that we have presented before, we obtain some corrective factor. So for example, for the capture of the plutonium 240, you obtain this kind of corrective factor that allow to go from minus 0.75% far from the experiment to practically zero. And one of the question about of this research was, will we learn something about fission yield with the assimilation of reactivity loss? It needs to be consolidated, but with in first order, we can say that we will not learn new information about fission yield with this kind of experiment, with this type of data that we have now. You will also obtain uncertainty reduction for some energy range for some cross section, and you will obtain also new correlation for the covariance matrix. So, for example, in our case, you go from 7.4% uncertainties to 1.3% of uncertainties after data assimilation, mainly by correlate the 6 largest contributor to the reactivity loss. So the question, in yellow, you will have a highly correlated value for parameter, and in blue, highly anti-correlated parameter. So it was before data assimilation, and it's after when the covariance matrix has learned about the reactivity loss experiment. So we will need to respond to some classical question about data assimilation, about what's the physical value of those change. Is a correlation between capture of U8 capture and PU40 capture has any sense outside of the reactivity loss? The reactivity loss would be considered as integral experiment for nuclear data evaluation, or it can just be used for adjusted cross-section data library for engineering purpose. All of this question will need to be asked and will be further explored inside in the PhD manuscript. So to conclude, the development of future reactor has to rely on validated simulation tool with mastered and quantified uncertainty by going through a VVUQ process. So the new generation tools allow to extend the field of VVUQ to more complex configurations, so to power reactor. and it has been used for the Phenix reactivity loss and the DARWIN-FR code package. With the current data library that we are using, we are and data assimilation, we are coming from 7.4 nuclear data uncertainty to 1.3% uncertainty after data assimilation with other corrective factor. And short-term perspective will be to assess those corrective factor. Is those corrective factor are fitting with current new nuclear data evaluation? And if we are propagating them to some nuclear data with integral experiment database, what's the impact of such a corrective factor on those database? With this kind of work, we could also tell something and orient further experiment towards some nuclear data. For example, if the uncertainty of the plutonium plutonium capture capture of the plutonium 240 is too high in a given energy range, we can orient some microscopic experiment to reduce the specific uncertainty, and probably also create adjusted cross-section, as I said, on purpose or for engineering purpose for a given targeted reactor. So, for example, for a future design based on sodium technology, we could use this experimental feedback to have a dedicated nuclear database based on the adjustment with the Phenix experimental feedback. And some other long-term perspective will be to perform the same exercise with other power reactor like Joyo, the Japanese reactor Joyo, or to use uncertainty quantification for fuel depletion, so fuel depletion uncertainty quantification with multiphysics for core design purpose in order to lower the different margins. So thank you for your attention, and I'll be happy to answer your different questions.
Thank you, Victor. If you have questions, go ahead and type them in the Q&A pane. And while we're waiting for questions to come in, we'll take a quick look at the upcoming webinar presentations in March. Overview of Canadian R&D capabilities to support advanced reactors. In April, multi-physics depletion and chemical analyses of molten salt reactors. And in May, a presentation that'll be a joint GIF IAEA webinar on regulatory activities in support of SMRs and advanced reactor systems. Victor, again, congratulations on earning the right to present on a GIF webinar. I think you are a perfect example that the next generation workforce will be in solid hands, and I congratulate you. It's clear that your work, it will be meaningful and impact a lot of people.
Thank you very much.
I don't see any questions coming in just yet. Do you plan to use data from Super Phenix reactor as well?
Data for the Super Phenix data was already used for fuel depletion purpose during my supervisor PhD thesis, and the conclusion of the fuel depletion study on Super Phenix was that it wasn't enough. Clearly not that it wasn't enough. So analysis with Phenix was really important on more stable power on a reactor with stable power was really important for reactivity loss and fuel depletion study.
That's a great question. Thank you.
But for data assimilation, for example, we can use some other integral experiment to constrain more the system, and maybe we can potentially use some data from Super Phenix or other experiments from Phenix too, like Profil, or for those who know all that stuff.
Thank you.
Yeah, and this is Patricia, and I see that you're planning for the future to maybe do something similar for EBR2 in the US or Japan with Joyo. Am I correct?
Yes, now that we have the formalism to perform such calculation, if we add the geometry and our isotopic composition for other reactor type, we can compare the results with our computational tools for those reactor and compute those sensitivities for this kind of analysis, but on other reactor, to see if we observe the same trends. For example, for data assimilation, if we observe the same trends for the same coefficient.
Very good.
Have you applied the calculation pipe to assess the performance of Jeff 3.3?
No, we have made every calculation with Jeff 3.1. Because why? Because further former work was for the Apollo 3 validation. I mean, was done with Jeff 3.1, 3.1.1. So to be sure that we are not that we are always good in some points, we keep this database. But the methodology is the same, and using this database or another one is not the same, but does not change mainly the methodology. We could perform this calculation with Jeff 3.3, for example, and see what happens if we have the same trends for sensitivities. Could be a great exercise, but I haven't done such thing in this work.
Thank you. I don't see more questions yet. If you have the time, Victor, we'll just stay on for a couple minutes and see if people are still typing in questions.
Okay.
Yeah, and people have the email address of Victor on the presentation, so feel free to contact him after the webinar. You know, sometimes it's a very, I will say, a pointy subject. You really need to be an expert. So feel free to share the slides also with others and contact Victor.
In my case, when dealing with data assimilation techniques, it's always difficult to provide specific feedback to the ND evaluators. Do you feel your work might be useful for them in terms of specific needs?
In fact, it was practically all the purpose of this PhD is to analyze and give a first approach on if this kind of experiment from a power reactor, which is a complex object, etc., can be useful for ND evaluators. So we will study a lot of configuration, and actually with this team to see and actually say something if it can be used for this kind of evaluation. So maybe the response will be no, but we see maybe the response will be that this kind of experiment will be only for nuclear data adjustment and no assimilation. But at this stage of the work, the purpose was to evaluate the possibility of using this for nuclear data assimilation, for example.
Thank you. Victor, again, thank you for sharing your expertise with us, and thanks for everyone joining. We have a lot of loyal viewers, and we really appreciate the support and the feedback.
Yeah, thank you for the invitation, and thank you for listening everything.
And thank you again, Victor. It was really good, and I shall see you in October, probably in London.
Yes, indeed.
So, and I echo Berta when I see all these people talking about nuclear energy and being at an early career. I think the future of nuclear energy is a very good hand. So thank you again, Victor, and thank you, Berta.
You're welcome. Thank you.
Thank
Have
you.
a good day, everyone. Bye-bye.
Have a good day, everyone. Bye-bye.
Bye.